Hello and welcome back. Lecture 7-1, Fourier Transform of Periodic Signals. The objectives for today's lecture are to describe how to find the Fourier transform of a periodic signal and then to provide examples of finding the Fourier transform of a periodic signal. Theory. Suppose x of t is periodic with period t naught. Then x of t is the summation from k equals negative infinity to infinity, x of k e to the jk omega naught t. We found that the Fourier transform and Fourier series are related by x of k equal to 1 over t naught, x hat of jk omega naught, where x hat of j omega is the spectrum of only one period or the envelope of the Fourier series coefficients. So what we see here is that Fourier transforms are more general than Fourier series because they can be used for periodic and aperiodic signals. So suppose x of t was a Posttrain. Then one period of that Posttrain would be a rect, and the Fourier transform of a rect is a sinc. So I'm going to sketch out a sinc here. And since this is the Fourier transform of one period, it will also be the envelope of the Fourier series coefficients. So that line is x hat of j omega. And this is called the envelope of the Fourier series coefficients. So the Fourier series coefficients would be here, here, here. So they're tracking the envelope of the Fourier transform. And we would call these x hat of jk omega naught, which is equal to t naught x of k, and we call them the samples of x hat of j omega. Using linearity, x of j omega, which is the Fourier transform of x of t, would become the Fourier transform of the Fourier series, the summation k equals negative infinity to infinity, x of k e to the jk omega naught t, which is equal to the summation k equals negative infinity to infinity, x of k times the Fourier transform of e to the jk omega naught t, which is equal to 2 pi, the summation k equals negative infinity to infinity, x of k delta of omega minus k omega naught. And for the next line, because we know that x of k is equal to 1 over t naught x hat of jk omega naught, we can make that substitution here. And 2 pi over t naught is omega naught, so x of j omega is equal to the summation from k equals negative infinity to infinity, omega naught x hat jk omega naught times delta of omega minus k omega naught. So the key takeaway here is the Fourier transform of a periodic signal are always scaled impulse trains, and that for periodic you're going to have the gaps between the frequencies, but for aperiodic you could have a continuous signal. So here we have a sketch of x of j omega. Notice it's the same as the stems from before, but they're now impulses instead. They're scaled impulses. So x of j omega would look like the following. They're all scaled impulses, scaled by the value of omega naught. And so on. Where this would be 0, omega naught, 2 omega naught, 3 omega naught, 4 omega naught. Negative omega naught over here, negative 2 omega naught. So one final thing to note. Note here that this would be k is equal to 1, k is equal to 2, and so on. So we can also say that T naught x of k approaches x of j omega as T naught goes to infinity or omega naught goes to 0. Example 1. An important periodic signal is the impulse train g of t. Find the Fourier transform g of j omega. G of t is equal to the summation from n is equal to negative infinity to infinity, delta of t minus n t naught. So first, let's make a sketch of g of t. It's just a simple impulse train where the area under each of the impulses is a 1, dot, dot, dot. And there's an impulse at 0, t naught, 2 t naught, 3 t naught, negative t naught, negative 2 t naught, and so on. So one period of this g of t would just be the impulse delta of t. And the Fourier transform of delta of t is 1, which is equal to g hat of j omega. So a quick sketch of that would just be a 1 for all frequencies. So now let's calculate g of k. We've done this before, but g of k is equal to 1 over t naught, the integral over t naught, 1 period, g of t e to the negative jk omega naught t dt, which equals 1 over t naught, the integral from negative t naught over 2 to t naught over 2, e to the g of t e to the negative jk omega naught t dt, which equals 1 over t naught, the integral from negative t naught over 2 to t naught over 2 delta of t e to the negative jk omega naught t dt, which equals 1 over t naught. So now if we make a sketch of g of k, g of k is going to be a stem plot where every stem has an amplitude of 1 over t naught. And the stems are located at k is equal to 0, 1, 2, 3, and so on, or negative 1, negative 2, and so on. Or in terms of omega naught, they're located at 0, omega naught, 2 omega naught, 3 omega naught, or negative omega naught, negative 2 omega naught. And what you should see here is that this represents samples of g hat of j omega, which is g hat of jk omega naught, where each sample is divided by t naught. So that gets us back to the equation that we had on the prior page. So now let's find the Fourier transform of the periodic signal, the impulse train. So g of j omega is equal to the summation from k is equal to negative infinity to infinity of omega naught, g hat, jk omega naught, delta of omega minus k omega naught, which equals the summation from k is equal to negative infinity to infinity, omega naught, t naught, g of k, delta of omega minus k omega naught, which equals the summation from k is equal to negative infinity to infinity, omega naught times t naught is 2 pi. So it's 2 pi g of k, delta of omega minus k omega naught, which equals 2 pi over t naught, because g of k is 1 over t naught, the summation from k is equal to negative infinity to infinity, delta of omega minus k omega naught. Notice you could also write this as 2 pi over t naught, the summation from k is equal to negative infinity to infinity, delta of omega minus k 2 pi over t naught. And so the last thing we're going to do is make a sketch of g of j omega. So the sketch of g of j omega is an impulse train. So actually, the Fourier transform of impulse train is an impulse train. And the impulses are located at 0, 2 pi over t naught, 4 pi over t naught, negative 2 pi over t naught, negative 4 pi over t naught, and so on. And the area under each of these impulses is 2 pi over t naught. Example 2. Find the Fourier transform for the following pulse train P of t. Notice that we also have g of t shown here because what you will find is that it is easier to find the Fourier series for g of t than for P of t, because for P of t you would have to do two integrals over one period because you would have values at 1/2 and negative 1/2, whereas for g of t you would only have to do one integral over one period because it's 0 for half of each period. So first, let's write the relationship between P of t and g of t. So P of t is equal to g of t minus 1/2. So the relationship between P of k and g of k is P of k would be equal to g of k when k is not equal to 0, and it will be equal to g of 0 minus 1/2 when k is equal to 0. The question is why? The reason is because the average value for P of t is 0, and the average value for g of t is 1/2. And so we can find that the average value, thinking about when we did this for Fourier transform, g of 0 is the average value for each of these. So for this one it would be 0, and for this one it would be 1/2. So first, let's solve for g of k. G of k is equal to 1 over t naught, the integral over one period of g of t e to the negative jk omega naught t dt, which equals 1 over t naught, the integral from negative t naught over 4 to t naught over 4 e to the negative jk omega naught t dt, which equals 1 over pi k e to the jk pi over 2 minus e to the negative jk pi over 2 divided by j2. And rewriting this as a sinc, this is equal to 1/2 sinc of k over 2. So then P of k would be equal to 1/2 sinc of k over 2 when k is not equal to 0. However, it's going to be equal to g of k minus 1/2 when k is equal to 0. So 1/2 sinc of k over 2 at k equals 0 is just 1/2. So you're going to have 1/2 minus 1/2, which equals 0 when k is equal to 0. So if we were to make a sketch of a sinc function, here we have our sinc, and this would represent g hat of j omega or p hat of j omega. And now we're going to take samples. So we take the samples here. And all of these samples here represent g hat of jk omega naught, and all of them except for the one at 0 would represent p hat of jk omega naught. because at 0, p hat of jk omega naught is a 0. So this one right here would represent that sample. Note that we can also say these are equal to T naught P of K and T naught G of K. So this is equal to T naught G of K and T naught P of K. Well, this one is the 1/2 here, so the one distinction would be right there. That would be T naught G of 0. So G of j omega is equal to 2 pi times the summation from k is equal to negative infinity to infinity, G of k, delta of omega minus k omega naught, which equals 2 pi times the summation from k is equal to negative infinity to infinity, 1/2 sinc of k over 2 delta of omega minus k omega naught, which equals pi, the summation from k is equal to negative infinity to infinity, sinc of k over 2 delta of omega minus k omega naught. So a sketch of G of j omega would look like the following. So here's G of j omega. And it's going to be a scaled impulse train, but the scaled impulse train is going to track the sinc. So we'll have a value here, values here, then it's going to hit 0, and then there'll be a value here, and value here, and so on. So these values at 0 is going to be pi, at omega naught is going to be pi sinc 1/2, at 2 omega naught it's going to be a 0, and at 3 omega naught we're going to have pi sinc 3/2, and so on. So then over here at negative omega naught, that would be pi sinc 1/2. So P of j omega is going to be very similar, but let's find that next. So P of j omega is equal to 2 pi, the summation from k is equal to negative infinity to infinity, P of k, delta of omega minus k omega naught, which equals pi, the summation from k equals negative infinity to negative 1. We have to do this to make sure we don't catch that term at k equals 0. Sinc of k over 2, delta of omega minus k omega naught, plus the summation from k is equal to 1 to infinity, sinc of k over 2, delta of omega minus k omega naught. And now let's make a sketch. So P of j omega looks just like G of j omega, except right here at the origin I have a 0. So here I have pi sinc 1/2 at omega naught, and at negative omega naught I have pi sinc 1/2. Then I have a 0 at 2 omega naught and a 0 at negative 2 omega naught. And then at 3 omega naught I have pi sinc 3/2. Same at negative 3 omega naught. Pi sinc 3/2, and so on. Example 3, double sideband radio. In radio transmission, we often wish to generate m of t cosine omega naught t, but the hardware actually multiplies by a square wave at a fundamental frequency of omega naught. The reason is because generating 100 megahertz cosine can be expensive, and a lot of times, such as in the labs you do in this course, the lab equipment has a maximum of 100 kilohertz, so it's difficult to generate a signal that quickly. The ideal method would be to use the cosine omega naught t, because the Fourier transform are impulses at omega naught and negative omega naught that are used to sample the signal. So now we're going to look at a different model that uses the Posttrain instead of the cosine. So the model looks like this. You have your message signal, m of t, that comes in and goes to the multiplier with p of t, and you generate the output equal to g of t equals m of t times p of t, where p of t is like a switch and has the following shape. What you should note here is this is going to be the Posttrain from the prior example. So it has an amplitude of 1/2 and negative 1/2. It's symmetric about the time axis, where the value here is pi over omega naught, and the value here is negative pi over omega naught. So the value here would be 2 pi over omega naught, and here would be negative 2 pi over omega naught. P of t is equal to a rect of t over pi over omega naught convolved with an impulse train, n is equal to negative infinity to infinity delta of t minus n 2 pi over omega naught minus 1/2. And looking at our model here, using our multiplication property for Fourier transforms, we get that g of j omega is equal to 1 over 2 pi m of j omega convolved with p of j omega. And p of j omega, and you're going to see that this is going to be the same result we got before, but I'm going to show you a different method to get there. P of j omega, using the multiplication in the frequency domain because it was convolution in the time domain, is pi over omega naught sinc of omega pi over omega naught divided by 2 pi times omega naught, the summation from k equals negative infinity to infinity, delta of omega minus k omega naught minus 1/2 2 pi delta of omega, which equals the summation from k is equal to negative infinity to infinity, where k is not equal to 0, of pi sinc of k over 2 delta of omega minus k omega naught. So now let's compare our two different radio transmission techniques. The first one is, assume we have a signal in the frequency domain, m of j omega, that has the following shape. It is band limited, and it has an amplitude of 1 minus b and b. And so if we send it through our original m of t times, where this was a cosine omega naught t, which means in the frequency domain it was at negative omega naught and omega naught, and it comes out the other end, we have m of t times cosine omega naught t, where the area under these impulses for cosine omega naught are pi. So in the frequency domain, using convolution, we would have 1 over 2 pi m of j omega convolved with pi delta of omega minus omega naught plus delta of omega plus omega naught. And so the output becomes copies of our message at negative omega naught and omega naught, where they both have an amplitude of 1/2. Using the switch or the Posttrain, we know that P of j omega has the following form. So we would have a pulse at omega naught and negative omega naught, but the train also continues. So 2 omega naught and negative 2 omega naught would be 0, but we're going to have pulses at negative 3 omega naught and positive 3 omega naught. 4 omega naught would be a 0, but then we'd have a pulse at every other frequency. And so this one has an amplitude of pi sinc 1/2, pi sinc 1/2. 3 omega naught has an amplitude of pi sinc 3/2. Negative 3 omega naught has an amplitude of pi sinc 3/2 as well. So now the output of my radio transmission system would look like the following. I will have the message copy at omega naught and negative omega naught like before, but I'm also going to have a copy at negative 3 omega naught and 3 omega naught, and the amplitudes are going to be scaled. So that means the copy here will be 1/2 sinc 1/2. The copy here will be 1/2 sinc 1/2. And the copy here will be 1/2 sinc 3/2, and the copy here will be 1/2 sinc 3/2, and so on. So these two here are our desired spectral components. And then the rest of the copies that go on both directions are called our undesired harmonics. And what that means is we need to have a method to filter those out. And we can use a low-pass filter to do this, and then use an amplifier to adjust it. So here, you would have your signal that comes in, that then gets multiplied by your Posttrain. It would then go through a low-pass filter, and we're going to sketch an ideal low-pass filter here where the cutoffs need to be at negative 2 omega naught and 2 omega naught. And remember, negative 2 omega naught and 2 omega naught would be here. And then it would go through an amplifier to get back the desired gain of 1. So the gain on our amplifier would be 1 over 1/2 sinc of 1/2. So you multiply by that gain to get this back to 1. And so on the outside, we would have an approximation of m of t cosine omega naught t, as we did before. Note that for the cosine, this gain would have simply been a 2. And this concludes lecture 7-1 on Fourier transforms of periodic signals.